Question 43 asks the following. A quantum system has three energy levels, so three wavelengths appear in its emission spectrum. The shortest observed wavelength is 248 nanometers. Light with a 414 nanometer wavelength is also observed. What is the third wavelength? Well, let's sketch out the quantum system. And this is going to be part of our preparation step, okay? The shortest observed wavelength is 248 nanometers. That's got to correspond to the biggest possible energy transition that can happen, which means from the top state to the bottom state. Now we can also calculate the energy corresponding to 248 nanometers. That's a good preparation step. And we're going to calculate energies of photons in this way. We're going to look for the energies in electron volts, okay? The energies in electron volts are equal to 1240 divided by the wavelength in nanometers. That's our shortcut, okay? So 1240 divided by the wavelength in nanometers gives me energy in electron volts. 248 nanometers corresponds to an energy, if we work this out, of 5.00 electron volts. 414 nanometers corresponds to an energy of 3.00 electron volts. Okay? So that gets us everything we need to solve the problem. Let's let our lowest energy state be 0 electron volts. The highest energy state has to be 5 electron volts, 5.00 electron volts. It has to be because the energy of the biggest transition is 5 electron volts. It gives rise to a photon of 248 nanometers. So this is 5, this is 0. 414 nanometers is also observed. And let's just imagine that that corresponds to this transition right here, okay? This transition from here to here corresponds to 414 nanometers. So 414 nanometer photon comes off. That's 3 electron volts. That tells us this level has to be 3.00 electron volts. So the third possible transition is this, the 5 electron volt state down to the 3 electron volt state. This is going to correspond to an energy difference of 2.0 electron volts. Well, 2.0 electron volts corresponds to a wavelength of 620 nanometers. Okay? So that is the wavelength that we're going to find in the spectrum. 2.0 electron volts or a wavelength of 620 nanometers. Now you might be asking yourself, how did I know that this transition was 3 electron volts? It meant that this one was 2. Well, let's suppose I built the spectrum the other way. Suppose I said this. The initial lowest energy state, which we looked at, corresponded to 5 electron volt change. Suppose I assumed that this transition corresponded to 3 electron volts. If that was true, my states are this, 0, 5.00, and then this state will correspond to 2.00 because the difference is 3. That means the third energy would be from here to here. This would still be a difference of 2.0 electron volts, would still correspond to a wavelength of 620 nanometers, and so it would work out exactly the same. It doesn't make any difference. If I choose this level at 2 or I choose it at 3, the third wavelength in the spectrum is the difference from the two other energy levels, and so the result will be the same, and so this is our final result. We'll ask ourselves if this makes sense. Well, we have a 5 electron volt difference between the top and the bottom state. I also see a photon with a 3 electron volt transition. So the third possible transition has got to be lower. It's got to be lower because this state is closer to there. So we expect it to be a lower energy, therefore we expect it to be a longer wavelength. 248 is the shortest, 414 is next. The final result, which we're calculating for, should be a longer wavelength. That's exactly what we observe, so everything makes sense.